Good morning, everyone. Today is August 1st, 2020, and this is the John Chappell Natural Philosophy Society Science Chat. Welcome, everyone, and everyone who's watching on the live stream. Let's see here. This morning we have Ian Cohen. Good morning, Ian. How are you doing?
Good morning, Franklin. Good afternoon from here. Things are fine, thank you. I hope they are with you as well.
Excellent. Finally got a professional haircut the other day. They're letting us do that around here. Of course, probably you don't have that much problem with the haircut, I suppose.
No, I don't. Actually, I've been cutting my own for about 35 years now. There's not much left, but I avoid the barbers.
Well, then no big change for you then. All right.
That's true. Yes. As indeed the lockdown, because lockdown is pretty normal for me. You know, I don't have a very active social life. I occasionally do indulge, but most of the time I'm self-isolating. So it hasn't really been much of an impediment for me.
Yeah, for those of us who are intellectuals, it's like a dream come true. It's just like everyone has to join us now, right? Okay, we're not missing anything apparently now, right? If we
a dissident's dream, I think.
Yeah, a dissident's dream, right? Yeah, not a lot of change for some of us, right? Well, anything on your mind in science these days?
I'm not sure, Franklin, if you yourself are familiar in any way with the work of J.P. Wesley. He was referred to me by Dennis Allen. I don't know if Dennis is here today, but he's written this big tome on scientific physics and electrodynamics and induction and all the rest. He has some, rather innovative theories. I think actually I had a look at the table of contents, and I've thought about every subject that he's written about. Obviously not in the depth that he has, but it seems that he's deceased now, and his books have to be obtained from his widow, who I understand is in difficult circumstances. So she's trying to, make a few dollars from it. So I think like a standard book might be $80 or something. I sent her an email the other day, but I didn't get an answer. And Dennis said to me that perhaps she's a bit elderly and she's not into email, so I should write. But anyway, J.P. Wesley, electrodynamics, and so on. He is on Google, actually. If you look him up, you will find something about him.
Yeah, I'm looking at him. Look at his jpwesley.com.
He's American, or he was American.
Yeah. An American multidisciplinary theoretical theorist known for his study of quantum theory. So he's got it looks like a wiki page here, but it's under his URL here.
I think I got more information on his own URL than on the wiki page.
He's got a career to 1961. Let's see here. So, but you got one of his books or so?
I haven't. The one I was recommended was Scientific Physics, which is this large tome. That would be the first one I would get. And I in the absence of getting a reply quickly from his widow, I just started thinking about it. But I need perhaps to consider spending more time and investing in the book and maybe doing some work. Now, in somewhat revenge, I gave a reference to Denny to the work of O'Rahilly, Alfred O'Rahilly. Now, again, I don't know if you're familiar with that, Franklin, but that probably is on the Google as well. Well, Alfred O'Rahilly is actually a countryman of mine. He was the president of University College Cork in the south of Ireland, 70 years ago or something. But he wrote this huge tome on electromagnetics. It's actually available freely on the internet. I could give you the URL if you like. About 900 pages of deep mathematical physics, questioning everything. Einstein's relativity, he's not in favor of, and going into the basic elements of electrodynamics and attacking modern physics and so on.
Oops, just a second here. Sorry.
There's some noise there.
Just a second. Let me kill this.
Feedback.
All right. I'm still having some problems with my screen share.
But you could spend a long time, not only lockdown, you could spend years looking at O'Rahilly's electromagnetic theory, and presumably you could do the same looking at Wesley's.
Well, what do you think was interesting about Wesley's theories? I mean, there has actually been a lot of discussion lately about the nature of electromagnetic waves, specifically something called a displacement current. Have you ever heard of that?
Well, yeah, that's essentially the Maxwell introduction, which sort of gives a sort of a symmetry between electricity and magnetism, and results in electromagnetic waves being predicted by just combining the equations. Yes, the displacement current.
Let's see, I got Bob waving at me. So,
yeah, I just wanted to mention Wesley's website. I've put it in the private chat. My understanding, talking to his wife, was that the son was taking over distributing the books, and I think he's in the States. He has put up this website for James Paul Wesley's work. I don't know if any of the books are actually directly available through the website, or if there's contact info. I'm scrolling through it real quick now to see. Yeah, it looks like information.
Yes, this is the website I was looking at.
Right. Okay.
And, it doesn't give. I think it might give an email address that I used.
Yeah. But anyway,
yeah,
I have
Gabriel Wesley. Presumably that's his widow.
Yeah. But I too have gone through Wesley's work some years ago, got his books and went through those. It's quite interesting. He does a lot with Weber electrodynamics, that kind of thing. But he seems to also want to drop the acceleration terms within Weber electrodynamics. And I followed some of his calculations. Unfortunately, he made a mistake in one of his derivations, which, if he were still alive, I would love to show him, because you don't need to drop the acceleration terms and things work out very well in Weber electrodynamics. Anyway, just wanted to make sure people had that website address if they were interested, and his books are still available from what I understand.
And he seems to cast significant doubt on, what he would consider traditional Maxwellian electrodynamics and things like the Biot-Savart law.
Right.
Yes. Yeah.
Right. And there's another guy, Thomas Phipps Jr.,
I've heard
who's similar to Wesley in that he's providing a alternative point of view on physics and in particular electrodynamics. He has a nice book, Heretical Verities, Mathematical Themes and Physical Description. That's available through Amazon. But like Wesley, he's critical of the special theory of relativity. He's looking for alternatives to classical electrodynamics and etc. And just an interesting read, physics read.
And to check with you, Bob, because I think you might have been a minute or two after I was discussing this with Franklin. I'm just wondering, are you familiar with this very turgid tome by Alfred O'Rahilly? It's either called Electromagnetics or Electromagnetic Theory.
Right.
900 pages.
I am aware of it. I have a copy of it. I have not put the time in to go through it.
Okay.
Because it is quite excessive, yeah.
I've spent some hours just flicking through it and looking at certain sections. But it's a lifetime. We would be required to go through it all in detail. But it's freely available on the web as well.
Oh,
And
is
of
it
course,
now?
Going back about 80 years, he's quite remarkable in challenging Einsteinian relativity, and I think he has something to say about displacement current as well, and other things. He fundamentally dissents from the physics which was developing around the time that he was
Right.
writing.
So on this displacement current aspect, this is apparently my understanding, if we're talking the same thing, in the Ampere-Maxwell equation, the fourth equation of Maxwell, where it's the curl of the magnetic vector, the magnetic induction curl of B. There's an added term involving the time derivative of the electric field. That is what my understanding is of the displacement term that supposedly was added by Maxwell. What I read about that is that Maxwell added it in order to complete the symmetry of the set of equations and blah, blah, blah. But then I read in Professor Assis' book, Professor Assis, you may know, is very scholarly in that he goes back and finds and reads the original papers in classical electrodynamics. And I thought in one of Assis' books, he writes that he found that there's a letter by Maxwell to somebody where Maxwell says that he made a calculation mistake, and by correcting that calculation mistake, that additional term appears. And so it was not a consideration of the symmetry of the set of equations, and he didn't just pull it out of the air. Maxwell made a calculation mistake. We all do. And by correcting that mistake, that additional term appears. So it's then kind of funny to read textbooks that says it's the genius of Maxwell that he spotted that this term was needed to complete some symmetry argument of the whole set of the equations. No. It was just a guy doing the mathematics, made a mistake, found that he made a mistake, and then corrected it.
Sorry, could you just explain that a little more? I mean, roughly, what was the nature of the mistake, and why did he have to add this term to obviate that mistake? I think I get from what you're saying.
Yes, but unfortunately, I don't have that letter or whatever that writing of Maxwell was, and I can't put my finger on that reference in Assis immediately. So it's kind of from memory reading what Assis was writing about, and that Assis, as you know, goes and digs out the historical documents. And a historical document from Maxwell indicates that Maxwell admits he made a calculation mistake. And by going back and redoing the calculation, this term appears in the calculations.
That's the displacement current term?
Yes.
So he
And
didn't
so
have
the details of
current originally?
originally he made a calculation mistake. I mean, we all do that. And that term was absent. But he spotted that mistake, went back at some later time, of course, and finds that displacement current just falls out from doing the regular calculations, whatever derivation he was doing.
Yeah, but that's
Now, when I do it,
like an ad hoc kind of
that's right.
thing
Now,
that
when I do it, if you want, I could share my screen and show you. But when I do the calculation of the curl of B, magnetic induction term, that term, the displacement term, falls out naturally. It's there. You don't need to postulate it or add it in afterwards. In fact, by doing the calculation, you see that the left-hand side of the equation has to equal the right-hand side of the equation. You can't just say, oh, I think I'm going to add this additional term because I like it, or I think it will make the whole set of equations more symmetric. No, do the calculation explicitly. Calculate the left-hand side and you get the right-hand side. And if you don't, the equation is wrong. You just don't add things to equations willy-nilly. You just can't do that in math. So I can well believe that, yeah, he did the equation originally, had a mistake someplace. Later on, he does the calculation again and does it correctly, and this additional term shows up. Left-hand side must equal right-hand side. And
what is this left-hand side and right-hand side he's trying to make equal?
Well, I don't know because I'm not a historian. I don't know exactly what Maxwell was doing. And of course, Maxwell was calculating using component form and quaternions, not the Gibbs vector equations from Heaviside that we're doing now. So I can't match it up exactly with what we would do today. But as I say, when I do that calculation, the curl of B is equal to, and then I put in what B is. B is the curl of the vector potential. So now it's the curl of the vector potential. What is the vector potential? Put that in the equation and keep calculating and calculating. Eventually, you get the right-hand side of the equation, and it does have that displacement current term. It's just part of the mathematics. You don't add it in after the fact.
Well, I think that appears in Maxwell's book, Electricity and Magnetism. I mean, whatever the origin of it, this Cease discovered letter or something, Maxwell puts it down in the way you've put it down as a balancing. But as regards to symmetry business, I've done a bit of work on that. And I've gone a bit further, actually, because I postulated like an analog of the current density, which might be called an obstruction voltage density. I've forgotten what I called it in my paper, but and I indicated that at low frequencies certain terms go out, and at high frequencies other terms go out. But there is a sort of asymmetry between the two equations, and indeed that gives you the wave function, electromagnetic waves.
Well, Ian, do you understand what the wave equation is? Possibly to try to explain how they justify that?
Well, let's say now
the root of this whole thing. It's like there's this wave equation.
Yeah,
supposed to describe how electromagnetic waves propagate through void space as a series of electric and magnetic fields.
Yeah. I would consider it an interaction. I mean, I don't like the simplistic views that E causes H and H causes E, and I would consider it a sort of an interaction, and it's hard to say how the simplest explanation of it might be, because mathematically we just sort of get vector relationships between double curls, and we say you get the sort of Laplacian out of that, and that's equivalent to the wave equation basically. But you should be able to see it more heuristically, Franklin. That's probably what you're asking. You've put me a bit on the spot, but I think if I gave it a bit more thought, I might be able to, go into a class of youngsters who were interested in physics, but didn't have vector analysis in their arsenal, and explain how the wave equation comes. I think maybe the simplest way to look at it is that it's an interaction between the two fields.
Yeah, a couple of comments, if I may. The simplest explanation is that it's wrong. The derivation of the wave equation from Maxwell's equations. The reason why it's wrong is because there is a approximation used during the derivation, well, several approximations. And one approximation is that you're dealing with a plane wave. And if you talk to physicists, they will admit that there's really no such thing as a plane wave, because the definition of a plane wave means that it's uniform in a plane extending to infinity. There's no curvature to it. And they admit that that physically can't happen. And yet that's one of the assumptions that they must make during the derivation of the equation. And so
get back to that plane wave thing. I've never heard of that. I mean, is that like a wave that you can, like, say, draw on a piece of paper? Is it the plane and wave on it?
Well, if I can find it, I have a presentation which has some pictures of that. It's, for example, let's say that the quote unquote plane wave is traveling along the positive x-axis. Okay, and the way that they picture that, what they mean by plane wave, is that at any point along that x-axis, you cut the x-axis with a plane perpendicular to that axis. Okay, that is part of the wave front of a plane wave. Okay, but that plane that you're cutting the x-axis with is infinite in extent and perfectly flat. Then the electric field is in that plane, and the electric field vector is in that plane, and the magnetic vector is in that plane as well. But that plane is propagating in the positive x-axis direction. And as it's moving, the length of the, and the direction of the electric field vector and the magnetic field vector is changing as it's moving along the x-axis. But as I say in the derivation, there is that assumption that it's a plane wave, and that plane is flat and extends to infinity in the y and z plane.
Well, that still might be okay as a, I don't know, simplification.
Well, that's it. It's a simplification, not physically realizable. And the derivation of the wave equation from Maxwell's equations depends on that assumption. And that's one aspect of why I think the derivation is faulty.
Well, I think the derivation is faulty because these equations only exist in the presence of, say, real charges, moving real charges. And in the middle of space, there are no such charges to support electric fields or magnetic fields. That would be the first, that's always been my basic argument as to why you can't take these equations and then divorce them from their original derivations from, real magnets and real charges emitting real fields, right? That makes sense, right? If you have a charge, then that creates a field. You can write equations about that. But as soon as you take away the charge, you just cannot keep on using those same equations. Right? But yet that is what the wave equation requires you to do, because there are no charges to create the electric field. I mean, there's supposed to be an electric field there, but there's no charge that's creating it. And there's supposed to be a magnetic field there, and there are no magnets present. Maybe you could get the magnetic field from the time-varying electric thing, but still, there's no charge to create the time-varying electric field, I guess. But I guess the whole trick is that they're saying that, well, when the dog chases its tail, and the electric field is the result of the collapsing magnetic field. But it just seems.
But also, to get back to the plane, I mean, we frequently talk about plane polarized waves, and there's a convention there. Nowadays, we always talk, electrical engineers always talk about the E field being polarized in a particular plane. I think maybe previously they used to talk about the magnetic field. Now we talk about the electric field. Well, we know, of course, that the thing is spinning all over the place in reality, but we can resolve we can resolve the E vector into a particular plane at any given time. So in a way, it's a bit of an idealization, but I'm not sure if that's what you're getting at, because you were talking about this plane at right angles to the X axis.
I have a slide from a presentation that I gave, if you want me to show it, that illustrates quite well this plane wave aspect.
No,
How about it?
Franklin is happy. I am. Free to show
Franklin?
that.
Yeah, if you've got a picture, let's have a look and see what this.
All right, share
Plane wave thing
screen,
is about.
share screen, share entire screen.
Are you using Chrome to share your screen?
Google Chrome, yes.
Yeah, see, when I try and do that, it crashes. And I was working on looking this up this morning. Apparently, anybody who shares any screen on Google Chrome sometimes crashes, but unfortunately, no one seems to know what this problem is. So
Weird. Anyway, this is, I don't know if you can see it. Can you see my slide?
it says
It's a
traditional
little small, but we can see it.
transverse waves.
Right. So here I'm trying to show a just the electric, the E part, propagating along the positive x-axis direction, and then at any point along the x-axis you cut that with a plane, and supposedly the electric field vector in that plane is everywhere the same. It points in some direction. This happens to be pointing, for example, along the y-axis direction. But that is what they seem to mean by a plane wave. Now you pick some other point along the x-axis, and maybe it's pointing in the other direction, but everywhere in the plane cutting that x-axis point, the E vector field is exactly the same everywhere in that plane.
Yes, I think that's what I've been calling plane polarized.
Yeah, okay. Yeah. So that's...
Although I'm curious about your title here, which is Traditional Proof of Transverse Waves. So
Right.
How is this considered a proof of transverse waves?
Oh no, it's one of several slides that I go through the traditional derivation, mathematical derivation of the traditional proof of transverse waves. And what I do is then go into longitudinal waves and show why this proof of transverse waves is incorrect. That was part of, as I say, a presentation I did quite a while ago. So part of the proof is also to show that longitudinal waves cannot exist in Maxwell's electrodynamics. And I think this is a case that I'm showing now, which refutes that. Just take a source and move the source along the x-axis, maybe further away from the point of interest or closer to the point of interest. And when you do that, you will get an electric field in the longitudinal direction along the x-axis. And it varies. It's oscillating. So, I don't quite... I can follow the math, this traditional proof of transverse waves only. I understand that, but it's incorrect to then say that, well, transverse waves only is possible. And this is why I think in part that's wrong, but then mathematically I can also show why the traditional derivation of transverse waves is wrong.
Now, some people think
Anyway.
that the electromagnetic waves travel like an earthquake transverse wave, a literal up and down of some material. Now, I don't know if I can at all agree with that. I think that just seems to be kind of a very naive way of visualizing a transverse wave. or
Yeah.
or what you were showing is that what's transverse are just these electrical vectors.
Yeah.
There's nothing, there's no literal up and down of some medium
Don't know.
that's there.
Yeah. Anyway. Yeah, so that back to the displacement, as I say, I can share my screen again. Maybe. Let's see if I want to do that.
Yeah, see, I still don't understand this whole displacement current thing. Now, some people are saying displacement current can be observed in a capacitor. So when you charge and discharge that thing, there's no actual connection between the two wires, but yet current can still flow. And some people are calling that displacement current. But that seems to be something totally different than anything that would be required to get an electromagnetic field to self-propagate. I mean, I'm not even sure, why do they need this concept? Because I can understand that you can get magnetic fields out of a time-varying electric field, and you can get electric fields out of time-varying magnetic fields, and that's how it's generally described. So why would you need anything else? You just say those two things and you should be okay.
Perhaps. Anyway, here's a paper which I've just put out on ResearchGate a couple of days ago. And in here, what I tried to show was that if you attempt a summary of Maxwell Heaviside electrodynamics, which I show here, I guess I can try to make it bigger. So in the approximation, all speeds are much less than the speed of light, and that time retardation of the fields is not considered. That is, the distance between the charge bodies and the detector is short. I tried to summarize what's Gauss's law for electric, magnetic, Faraday's law, Ampere-Maxwell equation, and then I go through the textbooks and define what the electric field is, the magnetic induction field, what the scalar potential function is, vector potential function, current density, written this way. So that's trying to summarize what I find in the electrodynamics textbooks. This set of equations is mathematically inconsistent. You can get a contradiction, and it's very simple to do using Gauss's law. You just stick in this equation, what E is defined to be, and then you stick in that equation, what phi, the scalar potential function, is. You do the calculation, you do not get just the right-hand side of that equation. Here I'm doing those equations. You get this equation instead, which has this additional term. And therefore, this Maxwell equation, divergence of E is equal to 1 over epsilon naught rho, is not correct. It doesn't equal just that unless you add additional restrictions. But when you look at the summary, there are no restrictions listed here. And that's why you never see this in any of the textbooks, this summary of Maxwell Heaviside electrodynamics, because it's mathematically inconsistent. However, you can make it consistent if you change this E in Gauss's law to be just the Coulomb field. And that Coulomb field is defined here, and the Coulomb potential is defined here.
So that's like the key assumption. You replace E with just its field. E is an actual charge, right?
Well, I'm using it as a field generated by the charge. You got a charge density function, and E can be written in terms of that charge density function. So these charges are either generating or is linked to or associated with these fields.
Yeah, that's my key, is because you've got to have these fields actually linked to actual charges. They just can't
Right.
exist in the middle of space. with
And they
nothing.
don't link it in these standard textbooks. And I think the reason why they don't link it in the standard textbooks is because it leads to a mathematical contradiction.
Yeah, you can't do that, which is what I've been saying the whole time. You cannot divorce the field from the thing that's generating it.
So anyway, if you do just make this little change here, that it's the divergence of the Coulomb field, and also in the displacement current, it's the time derivative of the Coulomb field, then this set of equations is mathematically consistent. But then if you do that, you cannot derive the wave equation, because in the standard way that they derived the wave equation. And that's because in the standard derivation, they have to take the divergence of E equal to 0. But it's no longer the divergence of E, it's the divergence of the Coulomb field. Anyway, this is a bunch of math stuff that I've been doing. Very simple to make a mathematically consistent version. But when you do it, you got to make these changes. And when you make those changes, you no longer have the wave equation in the standard way. You can still derive a wave equation when you introduce, for example, time retarded fields or time delayed fields.
In other words, if you just like break the laws of physics, you can do it.
Well, if you break the mathematical description of the physics, you can do it. It's all the mathematical description, and some people would say,
an additional term in the Ampere law, the Ampere-Maxwell law. So it's just maybe another formulation that you're coming to. You're separating the Coulomb electric field from what we call the general electric field, and then you're getting different terms. You're getting the Gauss law to be the same as the original, but you have an additional term in the Ampere law there.
Well, I think this is all a Disney fantasy land myself.
I'm sorry, Ian. I had to take a real quick call, so I had to jump off. But you were just as I was jumping off, you were making a comment about an additional term of something.
Yeah, Bob. I think you had an additional term on the right-hand side of the Ampere law.
That's correct, and that is because I don't have it up at the moment, but it involved the time derivative of the charge density function. You see, when you, I'll put this back up real quick here. Where is, I wonder if I closed it. Maybe I closed it.
There's Wesley again.
Yeah, I closed that. Excel, can't read much. Okay, here we go. When I do it, so it's this bit here. Can we make it bigger? All right, so this one in equation 46, that comes about, it's a time derivative of the charge density function. That comes about because I'm replacing a charge amount, for example, a time independent charge amount with a time dependent. See, if you start with the individual charges, these charges are not time dependent. It's the charge of like the electron or the proton. And this is for discrete sources. So when you then go from discrete to a continuous charge distribution or a continuous current density, you introduce the charge density function to replace these charges. I allow that charge density function to be a function of time. So everywhere there's a time derivative, I now have to account for the time derivative of the charge density function. And that is why there's this additional additional term in this equation. Now, under some conditions, they say, well, the charge density function is not a function of time, or we're not going to let it vary in time, and so that term just goes away. But you're right, there is that additional term as well. I'm sorry, did you add?
No, I'm just observing some things, and thank you for that explanation. I mentioned earlier, I'm not sure if you were here, but I introduced some additional terms which were symmetrical. I think what I did in my earlier paper on electromagnetic waves is in the Faraday law, I introduced another constant term, which was analogous to the current density, the mu naught JF and equation 46 there. So I've forgotten what it is, but it was something like I think I called it U. It was something like epsilon naught U, where U was I called an obstruction voltage density function, which disappeared at high frequency. But
Curious.
It was curious, yeah. But anyway, the conventional explanation, as you know, is that you get a wave function out of this, transverse wave largely, yes. And then some years later, you have somebody like Hertz who does an experiment with a spark gap generator, and he induces a spark in a receiver, which was some distance away. And that demonstrated, and that leads to people like Marconi, a practitioner, developing a receiver and a transmitter, and then introducing things like coherers to detect the signal, and resulting in the technology that we're availing ourselves of now, this very moment. So obviously that there is something in electromagnetic waves, but
right.
We're looking at it in different ways, and I can appreciate.
Well, what is it? That's the key question. Yeah. What is this electromagnetic wave? I mean, clearly it's a wave. That's how I can talk to you across the internet, because I'm creating sound pressure waves. They're being converted into some kind of electrical voltage, which is then being transmitted across space and wires as vibrations. So that's really the only thing we really know, is that it's a vibration. But other than that, what do we know?
And at the time of Hertz's experiments and Marconi and so on, you had other scientists who perhaps have been denied the accolade of having maybe introduced the first ideas for radio. People like Sir Oliver Lodge, who may have beaten Marconi to the demonstration, but he didn't follow it through, and people like Sir William Crookes. Now, they were eminent physicists, and they were looking at all this, but they answered the question that you've just put, Franklin, which was put at the time. They said, we don't know. And they postulated, actually, both Lodge and Crookes, that this might have been there was sort of a resurgence in the idea of psychical research at the time. And they were talking about telepathy. And they were saying that perhaps it's analogous to the human mind's communicating at long distances via telepathic means, and maybe psychic waves through the ether were similar to these wireless waves, and we don't really know. So we would consider that rather unscientific now, but that was quite a widely held view maybe at the end of the 19th century, beginning of the 20th century.
Really? It was psychic?
Yeah, I mean, they said we don't really know, and people like Lodge and Crookes were actually involved in psychical research. there was a resurgence in psychical research. I think one of them was actually simultaneously or sequentially the president of the Society for Psychical Research and also the British Association. So the prime scientific body and the prime sort of psychical research body. He held both posts, maybe not quite at the same time, but they were interested in psychical research, and he was saying that maybe the way we communicate through the ether via wireless communication is what we're actually using with regard to psychical telepathic communication, which nowadays we'd have much more skepticism about. So I suppose
psychic telepathy, that's also radio waves.
Sorry, say again.
So a psychic telepathic communication is also radio waves.
Well, I think that would be discountenanced nowadays, but that was the postulate which people like Lodge and Crookes were making in the 1890s.
See here, Dr. Lucas has a comment here. It says William Hooper measured 13 unique properties of 6 types of electromagnetic fields. The concept of charge is falsified by these experimental results obtained at University of California at Berkeley. I don't know how you can falsify the concept of, I don't know, charge. I think charge is a pretty obvious physical manifestation. I can take my comb and charge it up and it will attract things and repel things according to whether it's positively or negatively charged. And I think we can clearly see that electrons are charged, protons are charged. So I'm just not really sure how you could really falsify that. It's like saying I have an apple here and saying I falsified the existence of apples. It's like, no, it's right there. I can see it. I don't. So if you could clarify that might help out, because I just really don't see how.
And just a question, but Bob has put in the chat something about Danielle Finoro. Who is that person? Just briefly, and
he's a professor. Gosh, maybe in France, Italy. Sorry, yeah, and he's done a couple of books. For example, in papers, a full review of the theory of electromagnetism. And he has gone through, I think, very impressively, Maxwell's equations and shows where the differential equations do not lead to the standard wave equation, and how he modifies the equations so he gets a much broader range of equations and wave phenomena, not just plane waves. And I found his work very interesting. Probably look him up on the internet like everybody else, but it's an interesting read.
Yeah, I'm looking up his name on the internet. I don't see any immediate references to a scientific reference to him. I have to work on my stalking skills here. But did he conclude that the standard wave equation was a bunch of hooey, which is what I was trying to look for?
Essentially, and then he modifies it, and he does it just by mathematics. He seems to be very good at differential equations and wave equations. And
this is the problem, that all of this math is so complicated, and me being kind of a material guy, I'm just like totally out of my league. So I really can't prove that this is a bunch of hooey like I would like to. But maybe Danielle has basically done that.
It says he's a full professor of numerical analysis.
Yeah. See, I can't do that. I can't say that this doesn't make any sense. But oh, you have an Arbix reference here, so you can go look at that. Right? Although if he was really legit, he should have been able to publish in Vixra, right? Which is the official preprint source.
ARXIV, he's got something there. The electromagnetic nature of matter. ARXIV 12063110 V1.
Because I've been watching all of these arguments on the wave equation, on displacement current, and it all just seems like people arguing, you know, how many angels can fit on the head of a pin, right? And it's like the whole discussion just doesn't make any sense. You know, finally, I just replied, it's like, why should I believe any of this when no one has ever measured the electric, the magnetic, or the displacement current in a traveling electromagnetic wave? It's all a bunch of blackboard equations, right? Show me the experiment where I have a radio transmitter and I put something that measures magnetic fields and I see something varying magnetic, time varying magnetic field between the receiver and the transmitter. And it just...
But haven't they done that? Isn't that called an antenna?
No, it's not, because antenna will only tell you what the beginning and the end result is. It's
Right.
not saying what happens in the middle, right? Because
Well,
in the
that's
antenna,
fine.
all
That's
we're
fine.
getting is a time varying voltage. That's all we're
Right.
getting in the antenna. We're not
Right.
getting a magnetic field. We're not getting even an electric field. What we are seeing is a difference in voltage, which is just electron pressure, fundamentally. So there's no electric field, no magnetic field in that measurement.
I would have said it's measuring an electric field, but that's okay. And,
No, I
and
think
you're
it's
right.
measuring the
There's
electric
no
field.
measurement in between. I mean, it's only where the antenna is. What's in between? As I say, Professor Assis is very much an action at a distance. He says, here's a bunch of sources, and over here is a detector. That's it. There's no, that's all you have, action at a distance.
Yeah, but we want to find out what's going on, because we don't think it's just action at a distance. There's something going on here. You've got this antenna rod over here. What we're doing is shoving voltage into it. That's basically radio transmitter. And then on the other side, we have a similar rod, antenna rod, and we put an electric meter on there, and we can recover the signal that the transmitter is transmitting. And fundamentally, that's really all what we know, right? And if you put like a magnetic field detector in the middle of the transmitter receiver, you put an electric field detector, and we have those things, right? We can detect magnetic fields and electric fields. We have meters, you can do that. But between these two things, I think, I'm not 100% sure, but I'm pretty sure we measure nothing. There's nothing you can recover. It's like if you had if this were true, then you could recover the radio signal by just having, say, an electric field detector, right? It may not be very effective, but you should be able to recover the radio signal through just a pure electrostatic meter detector. I don't think that actually works. I think that you would detect nothing. The only thing that did that...
Isn't that what an antenna is? An electric field?
No, an antenna is not that. An antenna is just a piece of metal, and then when it receives the radio signal, whatever it is, it causes a varying voltage to appear on the antenna's terminal. That's different from an electric field detector. Like if I have a Van de Graaff generator, I can take one of these electric field detectors and I can detect the strength of the field. If I bring it up close, it's like 50,000 volts per meter. And if I take it way further away, it's like, 12 volts per meter. But that detects a static electric field, right? A rod antenna does not detect static electric field. I could put a rod antenna next to my Van de Graaff generator and, nothing. You attach that to the radio amplifier, and And I'm thinking you could vary the strength of the electric field and you would probably hear nothing. Well, I don't know that for a fact, but I'm just kind of, spitballing here. But I just want to say that what is the difference between recovering a specific electric field and a specific magnetic field versus what a rod antenna does. An rod antenna clearly does not receive, say, a magnetic field. I could wave my magnet around the rod antenna and I'd get nothing, pretty much, or maybe I get something, but it's clearly not the mechanism by which it's actually receiving a magnetic component. Or at least there's no way you can say that it's the voltage is varying in that rod because there's some time varying electric or magnetic field hitting it. That's just not, it just doesn't follow, is what I'm saying. I kind of suspect that I was kind of a physicalist, that I want all wave phenomenon to work the same. So I want all wave phenomenon to work just like sound through air, because I can see that, right? We know exactly how that works. So I like to think that what's going on between the transmitter and the receiver is something like a sound wave, right? In which case you have something that's vibrating this way, and it causes the receiver to vibrate in a similar fashion because it's literally being pushed and pulled by some medium that's in there, and not this mysterious somehow an electric and magnetic field leap off of the transmitter. Somehow they self-reinforce and self-propagate as a collapsing electric and collapsing magnetic field out in the middle of nowhere. Light travels to us from a billion light years away through seemingly, how does it maintain its coherence for that length of time, basically constantly being regenerated? I mean, anywhere along the way, it could have been, interrupted or something. And but if you think about waves as compression waves, those things can travel forever. Theoretically, if you don't have any frictional losses, a compression wave can travel those long distances forever, and the only losses they sustain are those due to geometric increases. An individual light ray can travel, like if you had a laser light or something like that, that can travel forever without any losses, as long as it doesn't disperse. If the light ray does not disperse, it maintains its magnitude indefinitely, which is kind of an unusual thing, right? But that's my little spiel on why I think this whole wave equation thing must be wrong. It's just a bunch of blackboard equations. I think nothing. Has no real physical significance. And I think the important part is that the mainstream is so satisfied with this wave equation thing that they're not really looking for the actual answer. I think the actual answer is out there, but it doesn't have anything to do with the wave equation. But as long as we believe that the wave equation explains this thing, then no one else is going to go out and find what the real answer is, right?
Well, there's no contradiction between the mathematics and the experiment. If there is, there's some problem there. I mean, to me, the wave equation is just one means of describing what's happening symbolically. And I mean, your analogy, Franklin, I think was fine, but you could do exactly the same for, say, a violin string or something, and you could work out equations with regard to the stress and strain in the violin string, and you could also work out its properties with regard to the density, the mass per unit volume, and how that's actually changing. And then if you combine those, you would get a wave equation, and you would get this wave, this sound wave coming out. And then if you had another violin string nearby, or maybe a better example would be, say, a tuning fork where you're getting a particular vibration and you had a string nearby, well, then you would get a sympathetic vibration, and that would be at short notice. And I think it's exactly the same that's happening in electromagnetic phenomena. And we may have to just decide exactly how we describe it and which types of equations, and whether we take the traditional Maxwellian analysis or whether we modify it. But I mean, that's the way I look at it. It's just a way of describing the phenomenon. Now, the one thing, you're right that the attenuation the attenuation depends on the type of disturbance that you have on the medium. But I my own view would be that there is always some attenuation, even in a laser beam, which is going through the ether, if you like. There would be an attenuation. It would be very, very small, almost negligible, but it does attenuate, and that's the sort of thing that I would say accounts for the redshift in the observation of distant nebulae. It's an attenuation in the ether of electromagnetic radiation. Very, very small, but nonetheless not zero.
Yeah, that would be another topic entirely. When you do have a light wave, that its frequency may actually stretch out as it travels further to the point where it actually will disappear. Actually, when the frequency drops to zero, then effectively it's gone. I mean, that's one solution to the paradox that the night sky should be as bright as daylight everywhere.
Yeah, the Olbers paradox. Yes.
Yes, that if light itself has a limited transmission distance, then that would alone explain, why is it we only see the local stars? We don't see all the stars from everywhere. So basically, not unless we think the universe is limited in size, but if it is infinite, then light must have a limited transmission range. So attenuated in that sense. So yeah, I would agree with that. There is some attenuation, but generally speaking, just a wave or one of these things that can travel very, very long distances. Like if I were in a swimming pool or something, and if I wanted to transmit something from one side to the other, Olympic-sized swimming pool, you could do that with a sound wave. You put an underground, underwater speaker in there. Probably the person on the other side could recover that signal and hear what you're doing. But if you're trying to, say, create a signal by, like pouring water into the pool, those kinds of signals don't travel very far, right? Or if you try to create like a tornado or whirlpool on one side and try to detect that flow somewhere in the other side, things that require the material to actually move are very, very short distance. But waves can travel very long distances because no material actually has to move. It's only just very locally there's a compression that has to move. But the atom from one side of the pool doesn't actually have to travel to the other side of the pool. Just its wave. So, and that's how we get super long distance phenomena. I think super long distance phenomenon must be wave phenomenon. But any phenomenon that requires an actual particle to physically move has to be kind of a short range kind of effect, I'm thinking. This is like kind of the differences between, say, a magnetic field and electric field. It's that the magnetic field forces tend to drop off a lot sooner than the electric ones because they think that the magnetic field has something to do with some actual particle being present to cause that phenomenon versus the electric field, which I believe is probably a wave phenomenon. That's why the electric field can travel infinite distances very quickly. So let's see. We've got the link to Daniel Ferrino's work here. So thanks for that. And let's see here. We've also got Alistair here today. But just to summarize, so we've been talking a bit about the displacement current, which I still don't really understand. I don't even know why they call it a displacement current. Seems like a weird name to give it. I mean, I can kind of understand it being a displacement current in terms of how they explain it in terms of capacitors, but I don't know how they got from what happens with capacitors to what happens out in the middle of space. Those two things just seem too different. And then even what we even call wave equation. I mean, why do we even need an equation to describe a wave? I mean, we know what a wave is. I mean, there's no wave equation to describe a sound wave, I don't think. It's more of a...
There is, Shirley. You know, this is where I come in with the analogy. You know, you can formulate an equation which will describe sound, and you might be talking about things like the the displacement of particles, or you might be talking about the local variation in pressure, and that obeys this wave equation.
No, I don't think that's an equation. I think that's just a physical description, because we know in sound it's physically just a compression and rarefication of molecular gas, right? Now, I don't know that.
Well, that's what you describe in terms of this wave equation. I know it's a bit analytical, but where the second derivative with regard to space is related to the second derivative with regard to time, and the proportionality constant is say the reciprocal of the speed of the disturbance. And then the solution to that gives you a periodic function. You know, it gives you something like a function of the coordinate plus vt, where v is the speed and t is the time, and coordinate minus vt. It's a periodic function. So that's all the mathematics is doing, really.
Well, certainly you have, say, the speed of sound equation, which depends on the you know, things like temperature and pressure and the
elasticity,
rigidity of the material. See, that kind of equation I can get into, right? That's just describing the variables involved in the propagation of, you know, said wave, right? But it's like this wave equation is some crazy thing where you're saying that there's this electric field and then there's this magnetic field, and yeah, I think that's all just kind of
in the first case. If you look at a string and you look at how it's being extended and compressed, and then you look at the variation in the pressure around it, and you work that out, and you take into account the mass of the string, and you work that out just by Newton's laws, basically, nothing more. Well, then you get the wave equation. You get the wave equation, and you get this constant of proportionality is exactly what you've said. It's the square root of I think the density divided by the elasticity. In this case, is the reciprocal of that, and that's all you're doing in the case of sound. Well, in the case of electromagnetism, it's quite analogous, as we've looked at before. I think both of us have looked at this, and you get exactly the same. You know, it's nothing really mysterious. But I do concede that if there is a conflict between the physicality and the mathematics, then there's something wrong. You know, they must gel together.
Let's see here. Dr. Lucas has a little comment here. And by the way, if you guys who are watching, there's 17 I see watching here. Great, thank you for joining. But if you have any questions about the topic, which is, you know, what is the electromagnet? Does anybody know what this thing is, right? Or can propose what this thing is if it's not this wave equation thing, right? So, of course, Dr. Lucas always points out that the electric field has tensile strength, even at great distance from the charge. The concept of charge cannot explain this feature. Really? Why not? I think the concept of charge doesn't have any problem with it extending tensile strength to great distances. And I suppose you have to actually give it a physical explanation for what it is before you can say that. And I would say that you can think of the charge as just like ringing. That ringing is coming off the charge, and it's going great distances. Like I said, anything that's a wave can go great distances. That explains the great distance part. And then there's the tensile strength business, and you get that because there actually has to be a physical medium between the charge and whatever is receiving the charge, so it can push and pull it, because it's literally, shoving it around. So, and that's where you get the tensile strength from. At least that's how I see it. But I would not say that tensile strength charge cannot explain that feature. It's like, yeah, charge can explain that feature. It can totally change that, explain that feature. Let's see here. Do we get someone else? Let's see. We have Cornelius and Harry joining us today. So, and Harry is our radio expert. So he's been very much involved in this whole discussion. And then you start getting to the things about, what's the ether, and no one's just figured out or discovered what this mysterious substance is, and that kind of complication.
I would comment on Dr. Lucas's charge can't explain the tensile strength away from the particle, and my take on that is the particle is actually a combination of mass and charge, and it's basically the mass that extends the tension within the particle out into the distance, and that the charge is basically a riding upon the mass wave. And my take on it, mass is basically a longitudinal wave that's focused to a point. And on that longitudinal wave, if it's not perfectly spherical coming inwards, then there will be a ripple, so to speak, on the spherical longitudinal wave, a dip traveling around the circumference of each individual wave, and that's basically the charge. And the charge is modulated on top of the longitudinal wave, because transverse waves require a boundary condition in order to propagate, and the longitudinal waves, high tension, low tension regions, provide that boundary. And so that's how I see it, that the charge is extended out into space, because it's actually riding on top of the mass wave or the longitudinal wave.
Well, I think what Bill is talking about is if you have like a positive charge, you have a negative charge, no matter how far you go, when you pull them apart, they pull back together. I think that's what we talk about tensile strength. I think that at no point does this like not ever feel this. It's almost like they're tied with a string or something.
Right. That's correct. But I mean, gravity has the same characteristic. Gravity extends out into the distance and gets weaker also at the same inverse square rate. So if you take gravity, which is the longitudinal wave, and upon that you modulate the transverse wave, the transverse wave amplifies or magnifies that gravitational characteristic, and it also gives it polarity. So you can actually not only have an attraction, but an apparent repulsion, which you can't have with gravity waves, because gravity by itself, a purely longitudinal wave, is strictly gravitational. Point to point, 2 points of gravitational wave locus are basically attracted to each other all the time. You can never get a repulsive gravity. But on the contrary, if you induce upon that gravitational wave pattern a transverse wave pattern, then you can get polarity because you have a transverse wave that can have a dip that goes inwards towards the center or a bump that goes outwards towards the center or away from the center, which can give you your polarization of increasing or decreasing a characteristic of gravity. And if it goes inwards towards the center, then it actually decreases the characteristic of gravity to such an extent that it will become repulsive. You go beyond. Gravity is always attractive, so any particle is always going to have a degree of attraction, and so that negative, the repulsive characteristic has to overcome the gravitational first, and then you go beyond that, and you can get repulsive characteristics. So that's where, that's where you get the electrical characteristic being much stronger than a gravitational characteristic because it concentrates because of that transverse wave pattern. But the transverse wave is not just simply going around in a circle. It's actually rotating in all three dimensions around the sphere of the longitudinal wave. And that's why
I'm not quite sure I really understand that. But the one thing I agree with is that the transverse wave can really only exist in the intersection of media, say, like in a water wave, you have to have the transition. There has to be some transitional spot between the water and the waves.
Well, that's where it becomes a longitudinal wave, has a region of high tension and a low tension. Or if you want to talk about compressional waves, you can talk about high compression and low compression. But in my view, the media is only ever tensioned. It's never compressed. And this kind of comes from a falsity of the Big Bang and everything. And it turns everything around. But intuitively, everybody is in tune more with compression waves than tension waves. So it's probably easier for me to talk about compression waves only because that's what people are in tune with, but not because that's really correctly what's happening, because compression waves don't give you the correct characteristic. But you still have an area of high compression and low compression, or if you want compression and rarefication. But that compression and rarefication, if that compression is perfectly spherical, then you have a surface, and if it's not spherical, if you can have make it egg shaped or something like that, where the wave front is egg shaped. Does that make sense? Where instead of being perfectly spherical, it's egg shaped.
Well, if I had an egg and I put a speaker in it, I could see that the waves are egg shaped.
Yes, you're right, exactly. Okay. But then each wave front, okay, now if you take that egg and you rotate it, so you take that wave front and you rotate it, then if you look at it from that standpoint, what you've really got is you've got a transverse wave, the surface of the egg, which is now not a solid device, but a wave modulation traveling around circularly around a central point. That is really like a transverse wave riding upon the longitudinal wave. That longitudinal wave is what gives you your basis for the transverse wave, which requires a boundary. The boundary being the maximum point of the compressional wave is a boundary. See, it's just like, so you understand that gives you the requirement of a boundary for a transverse wave.
I don't know. I don't really get that. Ian, are you getting any of this? This is all going. I'm not really sure I understand at all what Cornelius is trying to say here. I'm trying to desperately understand, but it does not sinking in.
I'm getting some of it, but I'd have to give a little more thought, to see whether the whole thing is coherent with respect.
Because I generally speaking don't think that transverse waves really exist in nature very much. They're not used very much. Doesn't really have anything to do with polarity or charge or.
Well, it exists, like, for instance, in seismology and stuff like that.
Yeah, that's only one of the only places I will recognize transverse waves
Okay,
actually existing. Other
but-
than
But basically, it's still a disposition of the transverse wave has a boundary condition to travel on, right? And so you're going between high density and low density gives you a boundary.
no, that's not really a boundary. I mean, boundary is like between water and air. That's a boundary. Or
Okay,
like
but
rope
okay,
in the air.
okay, okay. Let's go between water vapor and air. Okay, and then let's just go between higher density and low density air. Let's go with heat waves. Okay.
Yeah, none of those are due to boundary conditions, I don't think.
No, but your heat wave is also a wave in a transverse wave. So,
I don't.
so you see
What do you
you say when do you really when do you,
Wherever there's a transverse wave, there must be a longitudinal component. And furthermore, do you think that whenever there's a longitudinal wave, there must be some transverse element to it?
yes,
I see.
but
transverse components will exist in, say, a longitudinal wave. I mean, that's kind of like how I see it. Like if you have a long rod antenna, like
Yeah.
this pen. If you were to imagine that, I put a speaker driver element on this thing here, and I drive it, then it will create, like we were discussing, like an egg-shaped wave. Well, in this case, it will generate a pen-shaped wave, right? The waves will primarily be coming off a sheets which are parallel with my pen.
yeah,
And
I understand all that. And what Ian
component.
What
If
Ian says is
if I
correct.
rotate this, then you will be able to detect that this wave is coming in a different direction, and you can detect and you could polarize, and you could detect which orientation this pen is by looking at the wave, the whole wave front. This is like a wave. I described like a wave crashing onto a beach. A wave is not just this one little thing you draw on a piece of paper. That's just this up and down.
But you just made a transverse wave. I mean, you just went up and down with your pen, and then you went out to the side with your hand, and you showed up and down. But up and down, if you're looking for up and down, like Ian says, up and down is actually a compressional wave going up and a compressional wave going down. Meanwhile, the compressional wave is expanding laterally from left to right as you moved your hand, and that's the transverse wave portion of it. So it's exactly as Ian says, all waves have both a transverse and a longitudinal component.
Well, no, if I was demonstrating that, then I did it wrong. I meant to say that this rod is stationary, okay? And it's vibrating. Maybe it's vibrating.
You said it right. You said it right. You're just not following what you're
I'm
saying.
saying that the transverse component is encoded on the wave front, which is this big long thing, where which is pointing this way. You see, the wave directs the transverse wave component is pointing in the same direction as the rod that generated. So if you were to represent by a vector, then this is the transverse component. Although there's nothing moving in the transverse direction, the only thing that's transverse is the whole giant wave front.
Your hand keeps going up and down, Franklin. Your hand going up and down as you're moving forward.
Okay, I'll demonstrate it this way. See, this is the wave front coming off the pen. It's not going up and down. Okay, it's coming like that. That's what it's doing. It's
yeah. No,
and the only transverse component is the fact that this thing is oriented up and down. Right. That is the transverse component because the wave is going this way, but the transverse component is at a 90-degree angle, which is
that's simply the orthogonal expansion.
Up and down this way. The wave is moving out that way.
That's right, and the
longitudinal wave. So
the up and down is simply the orthogonal expansion, because it's moving. Because what you're describing is moving up and downwards simultaneously.
No, I'm trying to eliminate that. Imagine it was infinitely long wire. So there's nothing.
So now you're back.
I'm trying to say that there's nothing moving up and down. Nothing.
Not,
Nothing.
so then you have,
All you have is a compression wave leaving the vertical transmission element.
okay.
Right? If I did anything this way, I only need to say that there is a continuous line going up and down the screen.
So what
There's
about
nothing
back?
actually moving.
What about back and forth in the room? How much depth does this have? You went up. Okay, it's continuously up and down. Is it also continuously away from you and towards you? Then is it a plane
No,
wave that Bob Gray talked about that doesn't really exist?
Imagine a balloon that you make stuffed animals with, right? And what you do is that you are pumping air in and out of that thing. The balloon is getting smaller and it's getting bigger, right? And you do that so that you get audible sound waves. You make a transmitter like that. Okay, so all I can do is just push the air out.
Okay, so now you have a spherical longitudinal wave.
Get these waves, which are just compression waves, which emanate in the spherical, well, not really spherically, but rectangularly away from the balloon animal rod thing. But, I'm just trying to emphasize that there's nothing moving up and down. The transverse component has nothing to do with anything moving up and down. The transverse component is just something you can recognize as the wave travels across the room, that it has a specific angle. That angle can be pointing anywhere, you know. Like if this is a transverse wave, it can move this way, but it could also be oriented this way. It could also be moving this way. That is the polarizable aspect of the longitudinal wave.
That's just linear motion you're showing. There's no wave action to that whatsoever.
No, this is a wave.
Okay. I'm not going to go in. We all know what a transverse wave is, except for you, apparently. Okay.
I'm just saying that there's no transverse wave. There's no physical thing moving up and down in this direction. All you have is the wavefront, which I'm representing by my map here, right? Wavefront moves this way.
Yeah. Yep.
Pure longitudinal wave.
There you go.
Could be moving this way. Pure longitudinal wave. And that is a detectable transverse component. So this is how you encode transverse component on longitudinal wave. You look at the wave front. This can go in any direction. In fact, you could have two of these things going at the same time, and you could detect, there could be one longitudinal wave coming this way, another longitudinal wave generated at exactly a 90-degree angle. You could recover both of these at the same time.
May I join in?
Yes,
Can
James?
I join in for a moment? Hi, Franklin, and everybody. You may know that the Binary Mechanics Lab simulator provides exactly what is occurring between the the transmitter, where quanta are injected on one side of the simulated volume, and the antenna, or sensors, I call them sensors, which detect the arrival of the signal. I'm just going to call it a signal now, at the other side. And this has the advantage of the usage of the only set of time development laws known in physics that I'm aware of for a system state, which can derive the speed of light, which is no small distinction. Okay. Now, with the the point I wanted to make is that with the Binary Mechanics Lab simulator, and by the way, you can look at how this works in the paper Light Speed Derivation, which was recently posted on the Binary Mechanics site. You can save the system state every single tick, and then it's a 3D matrix of quanta. And you can then analyze exactly what's going on between the signal transmission and the sensing antenna, if you want to call it an antenna. I just call them the sensors at the other side. So there's actually no mystery as to what's going on between the signal broadcast and the signal reception by the sensors on the other side of the simulated volume. You
But
can
this is
actually
your simulator,
see
right?
that state every single tick, and using other software, analyze that system state. And by the way, if you just look at the simulator, you can see the quote unquote wave, or let's just call it a signal, transversing the space between the emitter side and the detector side. You can actually see it, say, in an X-ray view of the simulated space, but that doesn't get down to great detail. You can even do a different kind of experiment. You turn on what I call the right and left guns. The
Can
guns are
I
what
just
are.
ask that we just keep the discussion to reality rather than, because when we talk about your simulator, and I think it's a great thing, James, but you're the one that understands your simulator, and the rest of us don't have your simulator. The rest of us have the real world to deal with. And so when we start discussing how the quantized bits work, that adds not simplicity, but another layer of complexity, because now we have to look at how does this simulator really work, and how does that relate to the real world when we don't even have an agreement on how the real world works yet. So I'm thinking going into the specifics of the simulator is really not being a great help here.
Okay.
Does that make sense? I mean, we're trying to discuss how physical reality works.
What's going on in the simulator are just simply the 4 time development laws of binary mechanics, which is just an extension of quantum theory, adding full quantization of
if we all
energy, space, and
if we
time.
all understood quantum theory and exactly agreed upon how quantum theory worked, then we could go to the next step in how your simulator emulates quantum theory and that. But the problem is, we're not even to the level of where we can agree what a wave is, let alone the details of a quantized bit. You see, so when you keep on going into your simulator, it only complicates things, not simplifies things, in my view.
Well, I think it's just being presented as a possible solution, right? You have your simulator. Now, there is some question as to whether we believe your simulation actually means anything. It could just be an interesting computer program that doesn't have anything to do with physical reality, or it could represent
interesting computer programs. You're quoting articles on ArchiveX and so forth. Interesting computer programs are used throughout physics and other sciences as well to simulate situations. And all I can say is, I don't know, there is no other physical theory that has derived the speed of light, which is one of the most important unexplained.
There's plenty of dissonant theories which derive the speed of light. You'll find like 6 of them at least. So.
I'm not aware of even one. If you have even one, I would like to see it. So let's just start with one.
Electron C. Simony has done it based upon. You have to start with the density calculations based on the
salt crystal.
Because basically you just have to get the density and what's the other thing?
Elasticity.
You justify those 2 things, and then you say the light is a wave, and you can get the speed of light. You just have to justify those 2 things based upon things like charge, the strength of charge, and stuff like that.
Or the co-rush.
Well, see, that's not a derivation of speed of light. That's what you're stating a falsehood. You cannot use other unexplained data such as charge. And when you mention mass, when you mention density, I assume you're also including other physical constants with regard to mass per unit volume, right? And so those are not derivations of anything. What they are showing for the people who are math aware here is that there are relationships among these unexplained data, like the mass of the electron, the mass of the proton, the speed of light, the Planck's constant, etc., etc. But all of this is unexplained data. And so if you can show there is, if there is one, please email me and I will publish it, because there is no derivation of the speed of light or any other constants, Planck's constant, the mass of the electron, and the electric charge, which does not depend upon some other unexplained data. And so there are not derivations. What they are is showing that there is redundancy within this body of unexplained data, which we call collectively the so-called fundamental constants, that there is correlations between the different values of this body of unexplained data. This is the greatest body of unexplained data in physics. And so it's not a trivial matter when one can derive these values without reference to any of the other values. Okay? That is a true derivation.
You have to have a reference to a single value. Even in your biorhythmic mechanics, you reference your cell to a specific amount of energy or a specific amount of something, and from there you just divide, you just create ratios or just determine ratios of this. Many of these cells represent this characteristic. You still begin by taking reality.
Those are the primary constants.
That's correct.
And those have the status of postulates. Those have the status of the first principles of full quantization. If you quantize these three units of measurement, mass, length, and time, there obviously is some value in kilograms, meters, and seconds for each of these quantized values. But those are first principles.
You just use kilograms, meters, and seconds, which is constants. So you take those kilograms, meters, and seconds and say, this unit of my emulation is equal to this quanta of energy. So you basically just took the quantization that's the real world and said, this one is equal to a quanta one is equal to a qubit one. And so you're still saying, all you're doing is just changing the name of the value to your particular emulation. So it's not that you're deriving anything from anything.
I disagree. The number of so-called fundamental constants is greater than 3. And so we know there's interrelationships among this body of unexplained data, because people write equations all the time, and Franklin referred to them as in terms of one of these constants, like the speed, in terms of the others. But if you reduce
the number of fundamental constants is quantum or constants is greater than 3.
I mean, this is a matter of where you start. I mean, I could say that the fundamental thing.
You agree that the number of fundamental constants is 3?
Yeah, I think we can get it down. I think we can get down to as few as 3.
Yeah, 3 is good.
Well, great. Then we're in agreement. You got no problem with what I'm doing then. Great, wonderful.
I do have a problem with what
that's the first time I've heard someone say that. Because if there are only 3, go ahead. Sorry.
I'm saying that we don't have any problem with that. I mean, that's perfectly sound, and you can derive the speed of light from that. But other people have derived the speed of light. You're complaining about that they can't quite go down to your 3 constants. But that's just as a matter of where you start your postulates. As long as your postulates start in something which is, justifiable. So, for example, this theory I'm talking about, Simoni's Epola theory, starts with the existence of the electron, which I think is a fairly solid starting point. We may not know exactly what an electron is, or where it comes from, or what it's made out of, but we know or mass or length.
Well, if he's, with all due respect, Franklin, if he's starting with the electron, presumably he's starting with elementary charge. That's unexplained data. That's not a fundamental
Yes,
constant.
but
That's unexplained data.
It
So
doesn't
he's
matter.
using
You don't have to
unexplained
explain
data
it.
to relate to other sets
We
of
don't have to
unexplained
explain
data.
it. It's measured. It's like if I were to build a theory out of the existence of apples.
Well, of
I
course
do
it's
not
measured, but it's
where apples come
unexplained
from.
data.
So what? It's not. I don't care if it's
So what?
unexplained. If it's
Okay, so
there,
we don't need
you don't have to
science
explain
that
it.
anymore.
Right? That's my point.
Well,
If
the
it's
so what
there,
attitude is
you don't have to
totally
explain it.
contrary
Can
to
we
the whole
slow down a
purpose
bit
of
here?
this discussion.
Can we slow down a bit here? Because I think we're getting way off track anyway. But just let's take a breath.
Okay.
Maybe Ian, have you got anything to kind of share at this point? Because it's kind of we're running away here. I think, don't you, Ian? Or don't you also think so, Franklin?
No, I think it's getting kind of interesting that we're talking about the basis of our theories.
Yeah, we're getting into some other maybe philosophical concepts which we can agree or disagree on, and it might boil down to the question as to whether some of these constants could be different from what they are at present. For example, could the electronic charge be different? Well, conceivably it could be. It could be slightly less or slightly more. Now, that might mean that we would have a completely different world, or perhaps in the sort of fine-tuning example, we wouldn't have any world at all. So, to call that a fundamental constant, I suppose, is a bit arbitrary. Franklin said it was a measured value, and maybe that would be nearer the truth. I'm a little skeptical.
A measured value is it is unexplained why it has the value that it does have that is measured. Okay, that's what I'm referring to when I'm saying it's unexplained data. And this is the central, most important unexplained data in all of physics. In other words, if you're going to do physics, you would probably start with the greatest body of unexplained data that we have, which is why, the speed of light, measurement, charge measurement, Planck's constant, the so-called action measurement, etc.
Well, I think the thing is too that starting with we're talking about a constant here, and are constants really constant? Because when you go to the creation of the universe and you consider the Big Bang, you're going from essentially nothing to something. And the strength of gravity is changing, the strength of electric charge is changing. Those things were things that didn't even theoretically exist in the beginning, and they evolved. So can you really say they're constant, and can you really say that they're done evolving and done changing? So the only thing, I guess there's always this saying, the only thing that is constant is change.
I'm not sure I'd go quite that far. I think most of our constants stay pretty constant.
Well, the microscopic ones appear to be constant, but we don't know in the long term whether they are. And you're concentrating on microscopic ones. I mean, macroscopic ones, we don't know the explanation for either. Why is there roughly 21% of the atmosphere is oxygen? Is that a constant of nature? Is that just a coincidence? It could be 19%. It could be 23%. It's a macroscopic variable. So we don't look at it in the same philosophical sense as we look at, say, the electronic charge or Planck's constant or the speed of light. With regard to the speed of light, I mean, to me, it's a fundamental ratio between the magnetic and the electric interactions, as the Kohlrausch experiment would basically show. It would measure that speed of light as being the ratio between those. I don't know if there's anything magic about that. I mean, what is the explanation as to why it has that value? What is the explanation of the world? It's the same question to me.
Yeah, it's
well,
the biggest constant.
That's why I don't call them constants. I call them a body of unexplained data. And if you look at Appendix A in Physics, Appendix A, it's titled fundamental constants of physics. That
James,
is,
do have
I
a
think,
question for you.
propaganda. That is masking the fact that it should be titled Greatest Body of Unexplained Observations in Physics. And any physical theory that's worth anything at all has to deal with that. And it's completely masked by calling them fundamental constants. That's why I call them unexplained observations or unexplained data. And we can ignore the fact that these unexplained data should close our eyes and put like they do on horses, they put little shields to say, well, we're not going to see this unexplained data. We're going to call them something which is quote unquote given. And because it's in Appendix A of my Physics 101 book, and just ignore what is really the basic, most important problem in physics, to explain that data.
So
We're talking physics here. So James, I just wanted to ask you this one question, which is we're trying to explain what happens at a radio transmitter, where we know that the only thing that's happening is that we have a circuit applying variable voltage to a rod of metal. Okay, but I don't know that your simulator says anything as to how this varying voltage somehow leaps off of the metal rod into metal space, which is then the realm where your simulation applies. But what is happening in that physical realm?
Okay, well, as I stated, and I'll be very, very brief because I don't want to rehash things. The simulator allows you to save the system state, which is the position of all the quanta in the simulated volume, every single tick. Other software can then read those saved states, and you see exactly what's going on between the signal transmission and the signal reception over a volume of space.
Yeah,
so that the simulator allows you to see that. You don't have to sit around and debate what's happening. You can actually look at what's happening.
I'm not asking you that. I already admitted that your simulator will explain what happens after it leaves the transmitter rod and travels over to the receiver. But I'm asking you specifically, what is physically going on at the transmitter before that signal leaves? What causes the signal to actually leave based on a driving voltage? That's what we know. Physically, driving voltage, metal rod, somehow something leaps off that metal rod. How does it leap off?
It's called the unconditional bit operation, which is one of the 4 time development laws. Which these time development laws are the most effective set of time development laws known in physics today, as far as I know. If you know a thing better, contact me. I'd like to see it.
Well, I don't know of any other time development laws.
How about the Schrodinger equation? How about the Dirac equation? Those are time development laws.
Never heard them called that before.
Even Maxwell's equations, where there's a differentiation with respect to time, can be considered to be a set of time development laws.
Never heard them called that before.
We can pretend that we don't know what a time development law is, but if we're talking about physics, there's only 2 things. What is your system state, and how does it change with time? That's it.
Okay,
there is nothing more.
So if I look up time development laws, if I search time development laws on the web, what will I find?
Well, you'll probably find what all the losers have to say on the subject.
Well,
losers being that they aren't able to explain the fundamental constants.
So what you're saying is when I search time development laws, I will not find James Keenan on there.
I don't know what you find. I've never done the search, so go ahead and do it and see what you find.
Well, I mean, I just
you called it time development.
Explain anything other than development of time. Doesn't that all explain how voltage somehow gets transmitted to another circuit. That's no explanation at all, right, James? You can understand that, right? When I ask you how does the signal leap off the antenna, and you tell me time development laws, you can understand that is not any kind of explanation, not any explanation at all. There's no.
Well, it's the unconditional bit operation. I've already answered that question. We seem to be going around circles. It's the unconditional bit operation, which causes the bits to leave your broadcasting antenna.
So it's basically something
Unconditional bit operation.
it's basically something that only you have the definition of.
Well, everybody has it. It's been published for over 10 years, over 100,000 views.
If that were the case, I could search time development laws on the web and find something.
Well, you can certainly go to James's website. He's got
Great.
lots of
Go,
information
please
there.
do so. Time development laws. Go ahead.
I
Let us
would-
know what you find.
You say everybody knows what time development laws are.
I don't know what your point is.
So
your point is because Google doesn't give you the answer. That is your what we call popular vote on terms of what is logical and factual in physics is.
Cornelius's point is that your theories are
I think you're
your domain
that
in
attitude.
the mainstream, which is true. So if Cornelius wants to find anything about your time law development, he needs to go to your website, and he will definitely find it there, which is perfectly
I
fair.
guess people. No. I guess there are a few people here who are really well versed in quantum mechanics, what I call legacy quantum mechanics. That's prior to full quantization of space, time, and energy. I call it legacy, which has been around for many 50, 60, 70, 80 decades. And all of those books and treatises and all of the great minds, and yes, they were great minds, involved in quantum mechanics, which is involved in study of the behavior of the electron. It's used in nuclear physics to represent system states. There are time development laws. So that what you're basically saying is you don't know anything about quantum mechanics at all, which
what
is
I'm basically
fine.
saying is if I look up time development laws, you will not
Science is a
find
wonderful
time
thing.
development laws anywhere. Anywhere.
I mean, that would be a term that James is using. And
If there's a dt in the equation, the differentiation with respect to time, it's a time development law.
Your
Yes.
definition.
Look up Maxwell equations, dt in the denominator, and see if you see it. I did that really recently because I was wondering, are Maxwell equations a rendition of certain time development laws? And I was saying, well, I better look before I speak. And I did look, and yes, there's dt in those equations.
If you want to
Holy
look before
smoke.
you,
That's
you
what
want
we
to
call
look-
a time development law.
we're getting towards the end of the talk here, and we are kind of getting in circles here. So let's. I do notice though we do have some comments from Authentic Max. I think he's a new guy here, and he had lots of questions. But I'll have to tell you, Max, if you need to come early, we start at 7:00 a.m. Pacific, and these are a lot of great questions. But unfortunately, you asked it in the last 10 minutes of the chat here. So if you get here earlier, then we can entertain some of these.
Lots of interesting questions, Max.
So I'll give the speed round here. Okay, anyone else can comment, but most of your questions are about gravity and time. So specifically about the effect of gravity on light, and I would say yes, there is definitely a effect of gravity on light. We see that as gravitational lensing, and me personally, I feel it's a refraction effect, that the media closer to the sun is denser, and just like a real lens that we use in our camera, that difference in density causes the light to bend due to the differences in density. So it's not really a big, gigantic mystery. And one of the things that I don't think could happen with light is it could get like bent all the way back down to the sun, because refraction just doesn't work that way. You know, there's a limit to how much you can refract light. So that would be kind of my thing on that.
There is, of course, in addition to refraction, the possibility of light particles, if you like, postulated particles being influenced by the sun's gravity in the same way as any particulate medium would be, and that has been calculated as well.
Yes, that would allow the light to actually fall back into the sun, as opposed to a refraction effect where it could never really actually do that. Right?
No, actually, what you get if you do the mathematics again is you get a hyperbolic orbit, and this I would contend anyway, it would be the major reason, the major explanation of the light shift, the light deflection that was measured by Eddington in 1919. I think refraction is a secondary effect, actually.
And how about this question? This is a good one for James. Well, what existed before time? What creates time, right?
That's a question for me.
Yeah, he's asking about time. We were just
What
talking
creates
about
time? I have no idea. That's a step beyond my work.
what creates time.
My
I would
work, you know, if you're gonna, as Bill Lucas says frequently, in order to apply logic in physics and science, you know, you have to start with some principles, which are your starting point. You could call them postulates, which sounds a little bit pompous, perhaps. You could call them axioms, like a mathematician might. But you have to start somewhere. And I, where I'm at is quantizing the units of measurement in physics. I call it full quantization.
Right? So time is quantized.
And so, you know, what happened before things were quantized or before we were born? I'd have to read a history book to find out what happened.
Time, in my view, is nothing more than a measure of relative change, rate of change. It's the rate of change of one process compared to another. You have to have two changes, two processes changing in order to have time. You have to have one as a reference and one as a comparison to its rate of change. So that's time. Without change, there is no time. So time is fundamentally change.
Well, I think that agrees with the question here, which is, you know, doesn't the inertial motion of the smallest particles of elements create time? And that goes along with that if you have two smallest particles and they move at all, then yes, then you have an element of time.
That's one way of measuring time, but if it's change of anything, you can use anything as a reference for time. You just have to compare the two things.
The question in addition presumes that time had a beginning, that it's contradictory, that there was a period before there was any change, before this happened. Well, I don't accept that. To me, everything was eternal. Time always.
Yes.
Yeah.
Well, there could be God computer. I have an article on this, and that at some point God was in his garage, and he's building the universe computer, and that's what existed before time. And what creates time is actually that little quartz crystal he's got running on his motherboard, which starts moving the little bits in the computer forward, and that creates time. So that could be a possible answer.
But time, like everything else, is relative. It's relative to it's a relative rate of change between a reference and a measure and an object being measured, or a system being measured.
It might not be. If the universe was actually a big computer simulation, then time would be, especially for the digital computer. If it's analog,
if that's the case, then it's still relative to the main clock.
Yeah, it's still relative to the main clock.
So it's still time is relative.
The main clock sets an absolute time frame and the smallest bit of time.
Unless the clock is changing rates.
In which case we wouldn't know. But
exactly. So it's relative to that clock.
So the same for us in anyways.
Okay.
So in any case,
Let's go
so, we love questions, but like I said, we do start at 7 a.m. We go for 2 hours, and we will ramble on whatever you guys want to talk about. So, and if you got some questions, that's great. Better if we have more time that we can discuss it, because some of these can go the entire 2 hours, right? If you're talking about today, we were kind of talking a lot about the EM wave equation and what that means, and how waves travel across space somehow. And I think we saw a lot of evidence that would suggest that the EM wave equation, you just really can't derive it that way, that there is a lot of assumptions that might be going on here. That might not actually be correct. And that goes along with what I've always suspected, which is this whole EM wave equation is just a bunch of things on the blackboard and it's completely divorced from reality. But that's kind of what we spent most of our time discussing today. Once again, about the nature of light, how it travels across space, why is it at the speed it is, and the differences between transverse and longitudinal waves, and what does that mean, and what a plane wave is, and all the assumptions that Maxwell is making, which I think is making a pile of assumptions. But we're still left with the question of, what exactly is going on between the radio transmitter and the radio receiver in reality.
I think we're stuck with the question of what's a transverse wave and what's a longitudinal wave before we discuss anything about complexities of electromagnetic waves.
Well, we kind of got a little bit into that. So
I think we got to get a lot into that, because until we get a lot into that, until we understand what the difference in the longitudinal transverse wave is, there's no point in discussing a complex longitudinal or transverse wave like a gravity wave and electromagnetic waves.
Do you have a reference?
There aren't any transverse waves. That would be my opinion. I don't think that we need to discuss that, because there aren't really any transverse waves involved in any of these effects.
Cornelius, do you have any reference? I'd love to be reading it for perhaps next week.
Reference of mine? No, I don't have any references of mine.
Well, anything on these waves where you say that the transverse wave must have a boundary, and that it travels on top of the longitudinal wave. These kind of concepts are new to me. So if you had any kind of reference, I'd love to be reading about it.
Well, the only reference I've got is there was a conference call that we had probably about a year ago now, Franklin, where I had done some drawings, and I had shown the concepts of a longitudinal wave with the transverse wave being modulated on it. It was kind of a rush thing where Franklin wanted
I don't think we ever actually fully got into that. It was almost like we were just like scratching the surface, the top of the iceberg.
There was because part of that is that it was only like half the conference, and the other part of it is that you wanted to rush into the concept of a negative charge and a positive charge. Before we got there, we actually had to discuss what was a mass wave, a particle of mass upon which the charge resides, and so the intent was not to go that fast, but I think I kind of got pushed into let's talk about electromagnetics, where it was much more complicated. But the information is in there about longitudinal waves and transverse waves, and how waves attract each other and synchronize with each other. And then that's important. I don't know exactly what date that conference was, but maybe Franklin remembers or has an idea of how to find that and could share that with us in an email again, Bob. I can see if I can research it, but I don't remember exactly what date that was. That's the only information I really have that I've gotten kind of written down.
Okay, great. Thanks. I got to run. Thanks, everybody.
All right. Yeah, though I think that generally kind of explains what you were thinking about, how the tension waves work kind of thing. Not so much about, the transverse longitudinal. I'm still get kind of lost with that. But in any case, we have reached the end of our time here, and we can always discuss this, say, next week. Okay, always next week, next Saturday. So we start at 7 a.m. If you guys got some questions, we love to talk and debate. That's what we're just here for. For most of the times, a lot of times we don't have a fixed topic anyways. We're just like in the coffee shop and just discussing whatever comes up on your mind. All right, so that will do it for today's Saturday Science Chat. And like I said, hopefully bring your topics next week. All right, bye.